In this video, we'll going to discuss how we solve the Laplace equation. Now here, as you see, right, we will discuss from the very basic. Now, from the very basic means that all the viewers of this video, I will expect that you know only the little bit of ordinary differential equation from school level and little bit of partial differential equation, because we all know that, right? uh, the Laplace equation is actually the correlation between the partial differential variable, right, in the form of del u del x, del u del y, and all that stuff. So that's the very basic requirement to understand the Laplace equation. We all know that it's give us little bit of confusion how to solve and all that stuff, right? So in this video, we're going to clear all your doubts, but only one request is there. You should not skip, right, any second on this video. Just listen the approximate 1 hour video. Your all the doubts and everything on Laplace equation, I guess it will be clear. So now, in this video, right, whenever you see this, right, observe that first few thing, you maybe 80% of the student is or the viewers and well known about this fact, but here we discuss from that onwards. So here in this particular thing, we divide our lectures in 6 different aspects. First of all, we'll discuss little bit of ordinary differential equation, then we discuss the Laplacian operator, then Laplace equation, and most important thing, which is boundary condition. If you are an engineering student or a math background student or a physics student, whatever, right, this boundary condition may not be that essential, right, when you are going to solve a particular problem which will appear in your exam, because mostly the boundary condition is prescribed. But if you are talking about, or if you are learning it in the based of a research perspective, or maybe MS, PhD, and all that stuff, right? So then this boundary condition for your particular problem and how many boundary condition is required, why it's required. So that phenomena, right? It's very, very important. So that's why, right? We'll discuss that part as well. And then obviously the solution, and also we interpret it, right? That how we code the Laplace equation using MATLAB, and obviously that how we proceed and interpret the result, right? Because that interpretation also is required, right? So this all aspect we'll cover in this particular session. Start with the ordinary differential equation. What is the ordinary differential equation? We all know that a ordinary differential equation will be a function of x, y, and its derivatives, right? So here you see that I wrote it as y n minus 1, y double dash y. These are the derivative. So any function or any equations, right, with a combination of, right, its derivatives, right, it's called ordinary differential equation. It's well known. Now, for any differential equation, there is a unique term called order of the differential equation. What is that order? Order is actually the highest order derivative available, right, in that particular differential equation. Now, why are we discussing this order, right? It's not, you can say that it's not important here. No, it's very, very important, right? Because based on that only, we can choose that boundary condition aspect. So that's why we are discussing it here. Let's go ahead. So here, right, we consider few basic differential equations. So we just go ahead in the flow. So see that in this every differential equation, the first one dy dx equal to 5y. So here the order of the differential equation will be 1. Why? Dy dx is only available term. For the next one is d2y dx2. For the third one, right, it's again d2y dx2. And similarly, for the last one, you see that it's d3y dx3 is the highest order of derivative. Though we have a term that dy dx whole to the power 7. So we are not talking about this whole to the power 7 and all that aspect. We are only talking about that highest order derivative. So therefore, for the last one, the degree must be 3. And hence, right, we can write down the degrees of every differential equation, right? So that's the concept of the degree. Concept of the order. And the seventh for the last one will be the degree if it is looks like a polynomial, right? Though it's we cannot say it's a polynomial because polynomial I can't say that, but it looks like a polynomial, right? So in that case only we can say the degree is defined, right? That's you all know in school level. So here, what is the importance? What is the importance of this order? Because if we trying to solve a differential equation, right, with some particular order, then the solution must have that many unknown constant. So for example, if we solve the differential equation dy dx equal to 5y, and I wrote down the solution as y is equal to something plus C1 plus C2 plus C3. So some arbitrary constant, number of constant is 3, right? So then we don't say that it's a solution. It will be only called as a solution if it has only one unknown constant, right? So that's the concept. So as we say, right, that for a differential equation, there are two types of solution. One is called general solution, another one is called particular solution. So what is a general solution? For any differential equation of any order, right? So let us consider the order is n, right? So then if any function which satisfies the differential equation exactly contains exactly n number of unknown constant, that called the general solution. And it's obvious that that the general solution must satisfy the given differential equation. That's very normal approach, right? But what is particular solution? Particular solution says that, right, that any function in the form of y equal to fx, right, will be the particular solution, right, if that satisfies the equation. So in a particular solution, right, we should not have any unknown constant. But then how we identify the unknown constant? To identify or to find the values of the constant, right, we need some basic given conditions. And based on that basic given condition, we need to identify the particular values. So the basic approach, solve the differential equation, get the general solution, use the conditions on that, and then using those conditions, right, we'll identify the particular solution, right? So therefore it is the very crucial to remember, if a differential equation is of order n, so then to solve or to get the particular solution, we need n number of given condition. Now, what is the given condition? It says that suppose I'm taking about dy dx equal to 5. So they will give you two conditions, such that dy dx at x equal to 5 is 0, y at x equal to 7 is 5, or whatever maybe, right? So these are called the given condition. Now, this condition will be provided to you either in a linguistic form or in normal mathematical expression, right? So that's the only difficulties in differential equation in the solving process, right? So this is the basic of differential equation. Now let's discuss the next part. So for better understanding, we consider few differential equations, right? So first we consider a differential equation dy dx equal to y by x and dy dx2 minus y equal to 0. The first one is of order 1, second one is order 2, okay? Second degree differential, second order differential equation. Now let's go ahead. Here, first we find the general solution. So the general solution of this given differential equation will be y is equal to c1 multiplied by x. So here I'm saying that that's the true result, right? Now, if you want to verify, you can go ahead, take your pen and paper out and solve that, right? So do that separation of variable, like 1 by y dy is equal to 1 by y dx, integrate it, ln y equal to ln x, and go ahead as a normal approach, okay? So that's not a concern here. Now see that as here we have dy dx equal to y plus c1x, right? This will be the solution. Now it is obvious that if I add one more constant, if I add one more constant here, something's plus c2, right? It is obviously the solution of that given differential equation because it's a constant, right? It doesn't affect an in general, right? Maybe, right? But I'm not checking it that it is a solution or not. Be specific. But I'm saying that if I add C2, right? So at any cost, right, it cannot be the solution. It will satisfy or unsatisfied. That's a different aspect, right? But it cannot be. Why? Because it's have two constant and the order is one. So that's the basic concept. Okay. Let's go ahead. And now for the condition means that as we are having only one constant, we need one basic condition that is y1 equal to 2, right? Anything like it's a arbitrary condition I chosen for. So now if I substitute that y1 equal to 2, obviously we can solve the equation, the resultant equation for c1 and get the value of c1, substitute it, get the particular solution. So that's the approach. Go ahead for the second one, right? For the second one, the equation will be y equal to, right, c1 e to the power x plus c2 e to the power minus x, right? That we all know that this is, we can get it by the form of auxiliary equation, trial solution, and so on and so forth, right? So for the second degree, we can say that y equal to the power nx be its trial solution, and that's it, right? If you don't know that, you just put your view in our comments so that we can discuss that part also separately, right? But that's not the concern, at least for this particular video. So here we see that we have two conditions, that is y0 equal to 2 and y infinity at 0, right? Obviously I cannot write mathematically y bracket infinity is 0. We can say that it will be y tends to 0 and x tends to infinity. But for the normal approach, we just wrote it and it's okay, it's valid approach, okay? But mathematically it's not correct, okay? So now if we apply that, right, we'll get the solution as y is equal to 2 e to the power minus x, right? So this is called the particular solution, okay? So now understand that what is the particular solution, what will be your so-called general solution, and how to process, okay? That's it. So now the next important concept which will require to solve or understand the solution of the Laplace equation. That's the homogeneous ODE or the ordinary differential equation and non-homogeneous ordinary differential equation. It's not that difficult. Homogeneous differential equation means that, right? Well, it will be a differential equation, right, of any order or any degree, right, where the right hand side is equal to 0. Okay, so therefore no constant term is present in that stuff, right? So that's called homogeneous differential equation. For example, take some equation, right? See that y dash plus y equal to 0, right? So it's a non-homogeneous term. Y double dash plus ky equal to 0. It's again a homogeneous. So there are no constant term and separately, right? So that is called homogeneous. For non-homogeneous means that the constant is present, right? So for example, right, I take it as y dash plus y equal to x, right? X is not a constant, but still, right, it's a non-homogeneous, right? So it's not a constant, like a variable or the x independent variable will be present. Okay, so y double dash plus ky equal to sine x, and for the last case, see that y double dash plus y plus 5 equal to 0. So the right hand side is 0. Okay, but still it's non-homogeneous because it's obvious we're doing some basic arithmetic, right? It will be converted to y dash plus y equal to minus 5, right? That's well known, right? So these are called non-homogeneous ODE. So now we'll discuss the solution, mostly non-homogeneous equation, right? Concept-wise. Okay. Now we consider a differential equation, obviously. So here you see that a non-homogeneous because the right-hand side has a gx, non-discussing about the general aspect, right? Think of that example we just discussed earlier, right? So now to solve this kind of equation, we have to remember the solution always in the form of y equal to cx plus px. Now what is cx and px? Cx is known as the complementary function and Px is known as the particular integral. Now, what is Cx then, right? What is the complementary function? Complementary function is actually the solution of corresponding homogeneous differential equation. Now, what is the meaning of that corresponding homogeneous ODE, right? So here, if we consider, right, that our differential equation will be in the form of y double dash plus 5y is equal to 7x, right? Anything, right? So the corresponding differential equation states that it will be y dash plus 5y is equal to 0. So we forcefully make that right hand side as 0. Okay, and then we solve the equation. So that solution will be called the complementary function of the given differential equation. And the particular integral is actually the solution or some function which satisfy that non-homogeneous equation. Now, finding out this particular integral is not that easy. Okay, for different methods are there. For example, undetermined coefficient, variation of parameter, then that operator techniques and all that stuff, right? So if you need some lessons or lectures on that, please mention that in comments so that we can make that video, because these are all school level things, right? Or so that's why, right? Or maybe if you're engineering first year and all that stuff, so there you will already learn it. If not, inform us. Okay, let's go ahead. So now here we solve a proper non-homogeneous equation to understand the concept whatever we discussed earlier, because math is all about, right, solving a particular problem, and it's become more easier, right? So let's go ahead and take one basic differential equation. See that I consider y dash plus y equal to x, right? So it's a non-homogeneous because x term is present. But now how we solve it, right? So first we'll consider the corresponding homogeneous thing, right? So the x will be removed and it is replaced by 0, right? That's it. Now we'll solve this particular equation. So this equation, right, can be written as dy dx equal to minus y. Now see that this particular equation can easily be solved by normal separation of variable approach. Okay. So now this separation of variable in ordinary differential equation aspect, right, is actually we just change the variable, then we put the integration sign on both sides, or we integrate over the both side and apply the formula. So ln y is equal to minus x, and here the unknown or the integration constant is considered as ln k. Okay, so that the calculation is easier. You can go ahead with constant c, that's fine, right? Now, if we do the arithmetic or apply the operation on ln y, right, we can say that the y is equal to a constant c into e to the power of minus x. That's the solution of this homogeneous part. And that's why this is called the complementary function of the given ordinary differential equation, the non-homogeneous equation. So that's it. But now see that we need to find out the particular integral as well. So we actually take some techniques, right? This technique is called undetermined coefficient, right? And there are many more, so which is much easier, right? So in undetermined coefficient technique, it says that if my right hand side, right, is a function of x, so we'll consider our particular integral as ax plus b. If it is ax squared, if it is x squared is present, we'll wrote it as ax squared plus bx plus c, right? Something like that. Okay, you can see that, right? So now, as this is a particular integral, right, it should satisfy the given equation, right, that y dash plus y equal to x. So we can find the value. What is y dash or f dash, right? That gives me that ax, right, plus b differentiation, so it will be on the constant a. So therefore we can say that, right, that if I do this differentiation and do the basic arithmetic calculation, right, we find ax plus a plus b is equal to x. Now we have to equate both sides based on the degrees of that x, right? So they are, because it's a linear polynomial in both sides, so therefore the coefficient of each of the power must be equal, and hence we can say that a is equal to 1, a plus b equal to 0, and therefore we can say that a equal to 1, b equal to minus 1, and therefore my particular solution will be, or particular integral will be x minus 1, which is actually fx only, right? That's it. Now, whenever we found out that complementary function and that particular integral, so we can find that easily the general solution by summing up them. So therefore, general solution will be c to the power minus x plus x minus 1, right? That's it. Now we consider another type of differential equation, right? Which is actually we consider as y double dash plus ky equal to sine x. Again, it is a non-homogeneous stuff, right? But believes me, right, that you always remember that solution pattern of this particular problem. It is very, very crucial to solve the Laplace equation, because in Laplace equation, when we start with, right, in this video in a moment, right, so there that this particular type of equation will appear, and it will appear for every equation, Laplace equation, heat equation, wave equation, and everywhere. So if we remember this aspect, right, of solving, right, so then you don't have to remember anything, but I'll suggest that remember the final solution of this particular technique, right? So then, right, it will be much easier for you to go ahead and get the right answer for your exam, right? Let's go ahead. We don't discuss about that Laplace thing, and that first we understand the solution in the approach of a differential equation. Okay, let's go ahead. So here, as it is a second order, right, we have to go ahead and first consider the homogeneous part. So homogeneous part is y double dash plus ky equal to 0. Now here, k is a real number. So it can be positive, can be negative, or can be 0, right? So three cases are there. Okay, so this part you just remember. Now, first we consider the trial solution. What is trial solution? It's just an approach to solve this problem, or we are assuming that y is equal to mx is the solution. So basically, we are assuming that it's with corresponding to the x, it is harmonic motion. Okay, we just called it. Okay, so now as it is a solution, quote unquote, if we think on that prompt, so therefore y equal to mx will satisfy the differential equation. So let's go ahead. So here for to satisfy the given differential equation, right? So y double dash we calculate it as m square e to the power mx, and y dash is m e to the power mx. By normal differentiation, we can do that. Now, if we substitute that, we get it as get the auxiliary equation. So the auxiliary equation will be m square e to the power mx plus k e to the power mx is equal to 0. Y to the power mx is obviously not equal to 0. So we can divide both sides by that. So therefore, the auxiliary equation will take on the form of m squared plus k equal to 0. Now, obviously, the roots of this equation will depends, right, on the value of k. Because say that if k is equal to 0, m squared equal to 0, m equal to 0. Okay. And if we have k is positive, then m squared plus 5, right, will be 0. Now, m cannot exist in the sense, so therefore it will be complex number. If it's a negative value, m squared minus 5, so then it will be a real number, right? So then we have to consider three different cases. First case is m equal to 0, or k equal to 0. So here the auxiliary equation will be converted to m square equal to 0. That's obvious, and the roots will be m equal to 0. Now, when the m is equal to 0, we'll say that CF, or the solution of the homogeneous part, or maybe the complementary function of the given differential equation, will consider as y1x is equal to C1x plus C2. Okay. Okay. So what is that C1x plus C2? This is actually the way we will discuss that. Now, why so? We will always remember that if a auxiliary equation have two roots, right? Because any quadratic equation, right, have two roots, right? So here I consider that two roots will be m1 is equal to a, and the second root is m2, that's equal to b, right? Now, one possibility is that a is not equal to b. Okay, so if a is not equal to b, the solution will be c1 e to the power m1 c1 e to the power m1x plus c2 e to the power m2x. So that will be the solution. But if a is equal to b, okay, so therefore, we'll say that it will be C1 e to the power m1x, or maybe ax, you can say that, plus C2 into x into e to the power same m1x. Okay, so that will be the solution. Okay, so that's the general method, right? So here I use m1, m2, you can say that it will be ab. So that's okay. Now see that, right? If I consider m is equal to 0, okay, because say that m is not 0 is the roots. M is 0 comma 0 is the root. So here m equal to 0 is a root of multiplicity 2. Okay, so therefore we can substitute that m1x is 0, right? So it will be c11 plus c2x, right? So that's the solution. So here we wrote it thus in same form, just interchanging the name of the constant, right? So Always remember that for a auxiliary equation, if the roots are equal, right, unequal, the solution will be c1 e to the power mx plus c2 e to the power m to x, and if it is equal, right, it will be c1 plus c2x whole to the power multiplied by e to the power mx. Okay, that's it. So we get the complementary function in this approach. Now we consider the case 2 where k is less than 0. When k is less than 0, now here we consider the solution or the value of k is minus lambda square. Why? Because whatever the value of lambda you will provide it, right, you will always get a negative k, right? Because lambda is positive, so lambda positive negative, lambda square is positive, minus of positive is negative. Okay, that's why it's the general approach. So here the auxiliary equation will be m square minus lambda square is equal to k. Now, what is the solution or the roots of this equation? It is by default, it will be plus minus lambda, and these two roots are unequal. So therefore, the complementary function will be c1 e to the power lambda x plus c2 e to the power minus lambda x, where c1, c2, everything are constant. Okay, that's it. Now, we consider the remaining case or the third case, that is k is positive. When k is positive, greater than 0, so we can consider that k is plus lambda square. So when k is plus lambda square, right? So therefore, our auxiliary equation will become m square plus lambda square is equal to 0, right? Now it's a complex equation, right? So if I take that lambda square other side and try to find out the values of m will give us as plus minus I lambda. So here I is actually the complex I or iota, right? So now in that particular process, what will be the solution? Solution can be written as e c1 e to the power I lambda x plus c2 e to the power I lambda x, right? So something like this form we can write that c1 e to the power I lambda x plus c2 e to the power minus I lambda x. Okay, that's it. So this is a one approach. But this process, right, of writing in a I form, right, it's not that easy to proceed, and it's not looks good, right? So we can write it in the form of a cos and sine. Okay, how we do that? Because you remember, right, in school level you learn one important concept of which is called Euler's theorem, right? In Euler's theorem, right, we connect the exponential of thing with a sine x and cos x. So if we apply that, we can rewrite the solution as c1 cos lambda x plus c2 sine lambda x. Okay, that's it. So therefore, here we get the end of a different complementary function for a same equation based on the values of k. So if k is 5, what will be the answer? If k is minus 5, what will be the answer? If k is not there, that means 0, what will be the answer, right? So that we can compute from here. So just recall all the things. So the complementary function now we defined as yc, and that will be c1x plus c2 when k equal to 0. If it will be, what will happen if it is k will be less than 0, what happens, it will be k greater than 0. So when k less than 0, right, the solution will be c1 e to the c1 lambda x, c2 lambda x minus lambda x, and if it is greater than 0, it will be cos and sine form, right? So these things, it's very, very important to remember. Okay, so therefore we understand that, right, the complementary functions, right, of a differential equation of the form y double dash plus ky equal to sine x, right, it will be the same. Now I change it to sine x to cos x. I change it to sine x to x square plus 5x log x, whatever may be, right? The left hand side will be always same. So then the complementary function is always same. So if we able to remember this approach, right, or the final complementary function, right, so then we don't should have to repeat this, right? But obviously it depends on whichever level you are, whichever if you're a student, beginning of student, right? So therefore maybe in your teacher, in your college, in your university, the people or the teachers love to that you do this problem, then obviously you should do it, right? There are no such bounding. But if you are doing it for yourself, so therefore if you want to remember it, go ahead with that. So you can save a lot of time for that. Okay, but obviously, right, if the values of k, like if I give you that y double dash is equal minus k equal to minus ky equal to sin x, so therefore obviously the complementary function will change, right? So that also you have to remember. Okay, that's it. So now let's go ahead for the next step to solve this particular equation, or how to find the particular solution of this process. In this case, right, our next job is to do the particular integral. Now, as you've seen in the last problem, we saw the problem in that y dash plus ky is equal to x. So there, as the right hand side is in x form, using the method of undetermined coefficient, we use ax plus b as a solution. But here, as the left hand side, sorry, the right hand side as a form of a sin x, so we'll consider it as a cos x plus b sin x, right? That's the normal approach. Okay, so this is the technique, right? I'm not inbuilt it, someone else is inbuilt it for us, right? So we have to remember that approach, right? So let's go ahead. So here we consider the solution of the particular integral as a sin x plus b cos x. Now, obviously, this is a solution of the differential equation. So therefore, we need to calculate, right, that fx will satisfy the ODE. So therefore, f double dash plus a kf is equal to sin x, right? So therefore, we calculate that what is f dash. F dash is obviously a cos x b sin x, and f double dash will be a sin x minus b cos x, right? So let's substitute that value in the respective position, right? And collect, right, all the terms of x and y, x and sin x and cos x separately. So notice that here, this is the cos x term, right? So therefore, it will be ak cos ak minus b cos x. And if I take the sin x term, right? So therefore, it will be minus kb minus ka sin x, right? That's it. So let's go ahead and collect all the coefficient of sin x and cos x. Now, obviously, these two are equate. So therefore, if we equate the likewise term, we can find minus a plus kb is equal to 1, as well as the coefficient of cos x will be 1 separately. Now we can solve these two equations to find out the unknown constant a and b, right? So what is how we solve it? By the normal approach. So if we solve this equation, right, we'll get the final value as a and b, right? So that you can use your pen and paper and get it done. That's a very school level problem, right? Intermediate level problem, like very basic problem, right? So therefore here we get it, right, as a and b form, right? Now we substitute that in that particular solution, right, or particular integral. So therefore we'll get our complementary particular integral yp is equal to minus 1 by k square sin x plus k sin k cos x, right? So if I differentiate, right, that yp dash plus k yp, will obviously get the sin x. So therefore we get the complementary function, we get the so-called particular integral. Added them together, we get the general solution, and that's it. So this is an approach of a differential equation. But only one things you have to remember here, that complementary function obviously is not three types. The based on the value of k, the complementary function you have to decide, right? But here, as k is unknown to us, right, that we don't know that is it greater than, less than, and all that stuff, right? So that's why we choose the three condition, right? And this is crucial, right? So that's why, right, you just remember and take a time. If you want to copy that thing, take a pause and write down the complementary function. Okay, that's it. So therefore, we will use this to solve the next level approach of partial differential equation. So let's go ahead and write down the general solution, which we discussed many more times, right? So here, obviously the general solution had two unknown constant, and hence we need two boundary conditions for it. Okay, that's it. So this is the solution of this equation. Here we change the right hand side instead of sin x as fx, right? So the complementary function will not change because the homogeneous equation will not change. Okay, that's it. So this you have to remember. So if you needs a time again, right? I said few seconds only pause, so you just take a pause again here and either remember that, because this expression we'll use again, okay, or we'll recall it, right, when we solve the Laplace equation. And again, when the next videos will come out in picture, right, in heat equation, then it will be wave equation in different form, right, Poisson equation, and so on, right. So then, right, again and again, this complementary function is useful, and that's why we, in the first 30 to 35 minutes, right, we just discuss all the basics is required, right. Now, if you read it carefully up to now, right, so then the remaining part of the Laplace equation, you don't need to understand anything, right? You can solve it in a second if you only have a effort of calculation little bit. Then the remaining is very, very, very easy, okay? So let's go ahead and jump to the Laplace equation. So first, in the section 2, we'll discuss the Laplace operator first. Because see that we all know that what is Laplace equation. Maybe you heard of it, right? But how it's generated, right? The very basics of vector calculus, okay? That we'll discuss here now. So in vector calculus, right, few operators are need to be very, very important in this approach, right. First one is called grad, okay, that inverted triangle, you can say that, right. So in that is called grad operator, right. It's a vector operator. What does the vector operator means? It is actually says it's a summation of del x, del y, and del z, but obviously the I, j, k vector in three perpendicular, mutually perpendicular direction are actually attached to it, right? That's it. Now, next thing is called that, what will we call that, if u is a scalar field, that means u is a scalar quantity, right? And we will apply the grad operator on it, right? Now here it says that we are calling it operator. What is operator? Operator means that something which operates on some function, right? For example, ddx, right? So ddx is not a function, it's actually an operator. It operates on a function, right? So ddx operating on x squared, it gives 2x, right? So it's called operator, okay? So now, if u is a scalar field, so therefore grad u means that obviously del u del x, del u del y, and it del u del z, and the output is obviously a vector field, right? It's up here, right? So this operation of grad u is actually somewhat called it as grad u, or it's may called that grad operator applying on the scalar field u. Let's go ahead. Now here we consider a vector field here. Now, if it is a vector field with a component f1, f2, f3, so obviously it will be obvious that we cannot apply or cannot write grad f because it's undefined. So it should be written as grad dot f or grad cross f. Okay. So grad of f is called divergent of f, and grad cos f is called curl of f. Okay, just remember that. So here we write that either it's defined grad cross f because it's a vector, so either it will be connected to a cross product or a dot product, right? So the cross product is called curl, curl, curl of f, and grad of f is known as divergent of it. But here mostly we concentrate on divergent of f because that's the requirement in Laplace equation. Curl f, you will get that if you are in a fluid dynamics student, or you get it irrotational flow, right? So then we use that grad cross f, right? So and so on, like many more approaches there, right? So let's go ahead. So here, right, we go ahead and discuss that grad dot f, right? Obviously these are vectors, right? I don't use that vector symbol, right? It's more or less, it's not essential because we are in little higher level, right? Not in school level, right? But yes, it's better to use that vector arrow symbol above, not in grad operator because it's a vector operator, everybody knows, right? But it's better to use that vector notation in f. I just not use it. Okay. So therefore grad dot f, right? So grad dot f means it's a dot product. So therefore we can multiply that del x is operating on f1, del y in f2, and del z in f3. So therefore we can write down our grad dot f expression, and that particular expression is called divergent of f, or it's called div of f. Okay, that's it. So now we go ahead up to now. Let's go ahead. Now we'll compute another thing, that divergent of grad u. Now why we calling it or why we compute it? Let's compute it and then we discuss. Divergent of grad u. So what is divergent? Divergent means that it's grad dot F, right? So here we can say that it will be grad dot, what is grad U? It's grad sign of U, right? So grad dot, or yes, delta or grad dot grad U, right? So that we need to compute. So what is grad of U, right? We can say that for first grad operator, right? The grad before the delta, before the dot operator, right? It can be written as the vector operator, and grad U we already computed above, right? So it will be the dot product of this. So if it is a dot product, we can write it as del x is operating on del u del x, del y is del u del y, and so on, right? So this will be easily computed by the second derivative. So therefore, right, second partial derivative. So it will come back as delta u del x2, delta u del y2, and delta u del z2, right? So this is the expression of grad dot grad u. Now this operation, that divergent of grad u, we sometimes define it as grad square u. So grad square u, right? Grad square u is sometimes used and mostly used, but is actually nothing important in grad square. It's not that grad whole square. Grad square means that it's grad dot grad. Okay, but basically it is applying on some scalar field, right? And that scalar field application will be grad dot grad of u. So that's the only concept you have to remember. So now, whenever we talk about, right, that grad square u, this operation is called basically Laplacian, or from here only the Laplace equation is inbuilt. Let's go ahead. So this grad square u we have to remember, and this is called Laplacian operator in Cartesian coordinate system. Now in different field, right, we can talk about different kind of grad square expression, right? For example, we all know that there are Cartesian systems, spherical systems, cylindrical systems, spherical system, anything is there, right? A lot of systems are there, right? Elliptical systems are all there. So here, for different approach, right, or to solve different kind of problem, right, we have to define, right, the grad square operator in different form. For example, you are solving a problem in a rectangular domain. So obviously we'll choose the Cartesian system, rectangular or maybe cuboid system, right? It looks like that. Now, if you do in a cylinder, right? So then it's better to use cylindrical system. If it is a sphere, it is an spherical system, right? So then this operation will change. Now let's go ahead. So in polar coordinate system, right? First, right? This is the expression, right? So you just take a time and have a look on it, right? So you can take that x equal to r cos theta, r sin theta, do find out this using the chain rule in the second order derivative, you compute this form, right? So here we are not a time to discuss that. We just note down all these particular expression in different coordinate system, right? So mostly, right, this Cartesian and cylindrical system are mostly used, right? Obviously, the polar and spherical system is not that useful, right? But yeah, you can take a break and do whatever you want with that, right? For some particular aspect, maybe it is useful. So why we note down it here. So in this concern of this analysis, right, we are mostly concerned about that Cartesian equation, not the other two. If you or other three, right? If you need that, right, the solution in polar form, Cartesian form, a polar form, cylindrical and spherical form, put your name and mention in your comment. We'll obviously provide you the solution. But generally, we don't need it at this level of the basic engineering that level. Okay. In the higher level, if you're a researcher and all that, you want to learn it from our sites, and obviously you put a comment, we'll provide you the detailed solution of that as well. So here our main concern is to discuss the everything in Cartesian form only. So now, after spending a huge lot of time, we come back to this concept of Laplace equation. Now, what is the Laplace equation is all about, right? Let's go ahead. So Laplace equation is called a very basic simple form that's called grad square u, that means divergent of grad u or grad dot grad u is equal to 0. That's called the very basic equation in first of these lessons, that is Laplace equation. Now, this Laplace equation, obviously in the Cartesian 3D system will be taken in the form of del u, del 2u del x2 plus del 2u del y2 plus del 2u del z2 equal to 0. And in 2D system, it will come back as, right, del 2u del x2 plus del 2u del y2 is equal to 0. Okay, because this is the very basic expression for it, right? That's it. Now, why we need to learn the Laplace equation? That's very important here, right? So here we consider a few basic cases, right? First, steady state conditions, right? Or steady state system, right? So basically this Laplace equation describes the behavior of a field which is scalar, right? In a system which is unsteady. That means nothing is changing in the system. So that system, it can be analyzed by this Laplace equation, right? Only in physics, engineering, math, engineering field and all that stuff, this is a very important thing. It is used as equilibrium condition, static condition, something like that. So you can understand in the respective approach. Now then it will also be used in electrostatics, because we are talking about maths, right? So anything, right, we can describe, right, using maths only, right? So the corresponding physics, corresponding topics, right, the representation of the physical quantity of u will change, but the maths behind will not change. All are same. Okay, so you are something like that, right? If you are in air, or if you are taking a motion in a flight, right, it's aerodynamics, right? If you are in ocean dynamics, or whatever you call hydrodynamics, so the basic concept will not change, right? The equation maths will not change, but obviously the boundary condition, obviously the other conditions will change and makes our life maybe easy in other stuff, maybe difficult in other aspect, but that's a different ball game. But the basics equation will not change, right? So this thing is also being applied in electrostatics as well. So in electrostatics, right, the Laplace equation is actually basically called the potential, right? It is also say the potential of a electric charge, whatever machine, or whatever the force, right? I'm not talking about the physical aspect, but that can be solved using this approach, right? So here, right, also you can say that boundary condition, to find out the electric distribution in some field, right, is very crucial, right? So this boundary condition now coming back and forth again and again, and that we'll discuss in a moment. Okay. Now, let's go ahead and discuss another cases, that heat conduction, right? So heat flow of a body, right? So this is very important thing, right? Suppose there is a heat chamber or something, and heat flow, and how the static condition is achieved. If when the static condition is achieved, what is the temperature distribution of a plate, right? Those things can be analyzed easily by solving the Laplace equation. Now, obviously, that very important concept and widely used technique, right? That is fluid dynamics. So, wherever you go, you cannot leave the fluid dynamics, right? So that fluid dynamics aspect also, right? For we can understand the behavior, or the case of potential flow and all that stuff. Obviously, here it's not the aspect of discussing that. I'm just saying that why and where the Laplace equation must be used, right? So anywhere, right, from physics to math, from engineering to anybody else, medical field, anywhere, right? If you want to solve the realistic problem mostly, right, you cannot ignore the PDE and mostly the type of the solution in grad square phi equal to something, grad square k equal to something. So it changes, right? But the basic potential thing will not change. Okay, basic concept will not change. Okay, that's it. Now we'll discuss our concept, or the last concept, before approaching to the last leg, right? That's the solution of a Laplace equation. We'll discuss the very important concept of boundary condition, right? Because if you in research field and all that, you have to identify the boundary condition for your particular problem, right? Or if it is a project, right, then you have to identify the boundary condition. So that's a very crucial thing, right? If you want to say using Paxton, Nastran, ANSYS, Aqua, right? Whatever the software you want to use, right? Still, the basic thing, whatever you are learning here, right? That is already solvable by some software code, or the code is written by somebody else, right? But you have to define the boundary condition after doing some meshing and all that stuff, right? So for that cases, right, you have to understand the boundary. Obviously, for your particular problem, I'm nowhere to comment on that, and I cannot say that what boundary condition you want to use it, right? But here we are discussing the basic boundary condition, how many boundary condition is required, and so on, right? That's the main aspect. So here we consider the Laplace equation in a 3D coordinate system. And also here we consider that this particular equation or that our domain is defined on a cuboid, not anything else. Why? If it is not done in a cuboid or something else, right? Suppose you are in a room with a wall, right? It's not a plane parallel, right? Then can I solve this Laplace equation? Yes, you can solve it. Yes, you can define the boundary condition. But those cases, right, when your surfaces are not rectangular in the 3D, right? It's just like an arbitrary shape, like a parabolic shape or something like that. So in that cases, right, we cannot apply the analytical technique to solve this kind of equation. For that, you need to apply the numerical techniques, and we are not discussing the numerical techniques here. So that's why we forced our or we have reduced our concept only on this cuboid system. Okay, and this cuboid system is more or less fine. Why? Will come after when we go ahead in the interpretation section. Okay, not now. Okay, so here we are saying that we are defining it in a room kind of thing. It's a cuboid thing, right? So in a cuboid thing, obviously we know that, right? The general solution must have 6 constant or less. Why? Because we learned in the beginning of the differential equation case that if a differential equation has order 2, then it needs 2 constant. Now see that for a partial differential equation, we can't say that it's order 6, right? But think in that particular aspect, right? Del u del x2, del u del I2, del u del z2. For del u del x2, 2 constant, for the next 2, for the next 2. So that's why we need 3 different constant or 2 different type of constant is there. For del u del x2, we need 2 constant, and these 2 constant to find out, right, we need 2 given condition, and that 2 given condition need to be defined on the surface P1 and P2. Why? Because it is in x direction, right? That's why we need the boundary condition in the form of del u del x or the form of ux in x direction, right, in the surface P1 and P2, right? That's it. Now for del 2 u del y2, we need another 2 condition constant, but that 2 constant need to be defined, or the 2 condition defined in P3, P4, okay, or the right surface and left surface. If it is defined somewhere else, we can't solve it, okay? So that's the why the boundary condition is to define. So that's why if you see that, right, I want to define a condition, right, that u del u del y, okay, in this surface is I define del u del x is equal to 0, okay? So then we may not solve the problem, right? Or maybe it's a different approach, right? But here that del u del x condition need to be used to find the constant comes from del u del y2 only, right? That's the aspect here. So this is the crucial manner, okay, when we need to solve. Now let's go ahead and remaining condition. For that, we need to the top and upper surface, right? That P5, P6, right? So this two surface value is required to find out the constant. So here we need that, right? Or why we need that? That which constant need to be found out using what kind of equation and how many boundary condition you have to decide, right? So based on the order then, right, we need that much boundary condition. Now suppose, right, you are saying, right, that you go ahead with the analytical solution in whatever we are discussing here, and you have to impose, right, 10 boundary condition. So see that if I want to apply the 10 boundary conditions, so this particular method, whatever we are discussing in, obviously we cannot apply that, or we cannot solve the problem. It's something like that. You have in a system of linear equation of 5 variable, and you have 10 different equation. So you don't know we have a mixed solution or not, right? So similar case for partial differential equation or the ordinary differential equation. So if we have 4 differential equation, four boundary condition, Obviously, we have infinite number of solutions. If exactly 6, we get a unique solution mostly. And if we have more than 6 boundary condition, right? I'm not sure, right? We have to check for that particular problem itself, right? Not that in general approach. So the in general basic approach, right? We always solve the equation if we have 6 conditions. So you have to identify your problem, right? Or your domain in such a way that we have only 6 conditions. Then the solution will be easier, right? What will happen in more, what will happen in less, put your comments on that. We'll discuss on that comment section. Okay, that's it. Let's go ahead. So now, let's discuss in the 2D system. In 2D system, we are defined in a rectangle, obviously ABCD. And here from del 2 del x2, we have two constant. For del 2y del y2, we have two constant, and that's why total we need four constant, right? And to identify the or to derive the values of the constant of del 2y del x2, we have to use, right, the condition a along AB line, sorry, yes, along AB and CD, right? And in Y direction, if I need to find out, then we need to find that condition or define the condition along BC and AB. So based on that only, we can identify or we can solve any equation of this particular form, right? So that's the boundary condition in Laplace equation in 2D system, right? So now we go ahead and learn another exact way of that how the boundary condition can be provided to you for any PD not bounded to the Laplace equation, right? Here, whatever we are discussing, it's not true for Laplace only. It's anywhere, right? Let's go ahead. So first, we consider that rectangle of side A and B, right? So see that it is bounded by 0 to A, 0 to B, right? X equal to 0, X equal to A, Y equal to 0, Y equal to B, right? So in that particular domain, right, our Laplace equation is defined. Now we need four boundary conditions. So we consider the boundary condition specifically, right? So see that, right? We can define, right, that u1, u2, u3, u4, right? So these are some values, numerical values, or maybe the functions, right? Okay, now say that for u1, u2, right, are actually can be given you by a function form or maybe by a form of a constant. So maybe it can provide you that u1 equal to 0 or maybe u1 equal to sine x, u4 equal to 0 or u4 maybe sine y, right? Anything they can provide, or maybe sine x plus y. No, sine x plus y cannot be provided, okay? Uh, like it can be, but the not analytical solution will not be easy in that sense, right? So we are not discussing that aspect here, right? So here our u1 u2 must be the function of fx only, and u3 u4 must be the function of y itself. Now if it's a numerical value, obviously it's well accepted, right? So now let's go ahead. So therefore, it can be provided to you that u0y is equal to u1. Now, why we write that in that particular form? See that our solution, right, our solution will be in the form of uxy, right? Now let's concentrate on this line. So in this line or the y-axis, right, our x is always 0. So for all x equal to 0, for different values of y, our u0y or the value of this function in this y-axis must be u1. So that's why we wrote it as u0y is equal to u1. Similarly, if we talk about u2, right, our uay is equal to u2. That means when x is equal to a, for whatever value of y you supply, your value will be a constant or u2. Now, when I say constant, it can be a function of x, right? Sin x, cos x, tan x, log x, x plus y, x squared plus y, whatever may be, right? It's up to you, right? It's not our concern, right? But we are saying that it must be a function of x. If something else, yeah, that's a different approach. Okay, let's go ahead. So here, right, we consider that y equal constant, or the constant come from del 2y del I2. So therefore, it will be ux0 is u3, uxp is equal to u4. Now see that we are saying that our boundary condition is given only on, right, uxy and all that stuff. Why not the derivative is provided? For example, right, I'm talking about a temperature, right? I'm talking about a temperature, right? Temperature distribution. No, it's not a, I'm not talking about a, that this equation of Laplace equation is solvable using the temperature distribution can be solvable using the this gradient method or the Laplace method. No, I'm not saying that. I'm just saying that, right, for basic understanding of physical consequences. So for example, right, this is a hot plate, okay? This is a hot plate and U1, U3, U4 at the temperature, right? Now, I put a ice bird here. So this is a ice. So what happened then? If I put that ice, right? So then the temperature U1 or the T1 at the at this x equal to 0 is always be 0. Now I'm not saying that you don't think the physical consequences like you have to apply Newton's cooling law for that, this, that. No, I'm not saying that. I'm believing that if the ice will be put it in a plate, right, it will be 0. And it is acceptable because we are if I talk about Laplace equation, that's 100% correct. But for other aspect, no. Why? Because in Laplace equation, we called it a steady state condition. In a steady state means that if we put a plain heat plate, right, and one side is a cooling pad is there, right, or the ice pod is there, we are talking about after t equal to infinity. That means after a long time, then only the steady state condition achieved. But forget about those things, right? We will discuss in the interpretation section. Now, if one side is ice and forcefully I make it some mechanism and make it as 0. Now that is called that condition, whatever boundary condition is described, that U0, UAY and all that stuff. But now I consider a different approach and different particular problem. Think that some particle, some gas or everything is moving, right, inside that rectangular boxes, right? So here, right, if some particle is moving and give a force, right? So obviously you can see that if a particle comes here and we are discussing about the forces, right? So that force, right, or that particle should not leave, right, or will not leave the boxes. So what happened, right? The forces, right, in this direction, right, will become 0. Because if we have a forces in this direction with the component in the x direction is have some values, right? So therefore it will break the graph and must go away, right? But it's not happening. We are forcing that velocity in the x direction by some extra force, by the world, by external support or whatever. So therefore, in this case, we can say that the velocity in the x direction is 0. Now, when we say the velocity in x direction is 0, so therefore, del u del x must be 0, right? So the boundary condition can also be provided in the form of delta u del x, right? So let's go ahead. So therefore here the boundary condition can also be provided in the derivative of del x del y, right? Del x del y, del u del y and all that stuff, right? Now here also the values and u1, u2, I don't change it because it's all from given thing, right? That's it. Now notice that if your problem which is given in the form of only u, right? So then it's called Dirichlet's boundary condition. The pronunciation, whatever you want to use. And the next one, right, when the derivative is present, is called Newman boundary condition. So for different aspect, analytical solution will not change the pattern of the solution that much, right? And the procedure will not change. Okay. But for numerical approach, right, you have to your process will change, that whatever technique you want to choose. If it is a Dirichlet, obviously completely different. If it is Newman, it's something else, right? And there will be much more complicated condition, which is in generally you want to use, right? That's called Robinson boundary condition or mixed boundary condition. That means, right, someone may say that in this particular boundary, you say UAY plus del u del x of ui is equal to 10. Okay. So here you have Newman condition as well the Dirichlet's boundary condition. So then the solution pattern will definitely change. So but here we are not discussing those aspects as well. Okay, because obviously we are now seeing that we are narrowing our concept one by one, right? And it should be, right? Because in one lecture, we cannot cover every aspect of Laplace equation. It's not possible, right? Now let's go ahead. So here we consider that, now let's go ahead and solve the last section, right? That is how we solve the Laplace equation. Now see that if you're listening from the beginning, right, and if you're wasting your time if you think in that way, but still, right, if you are in the from the beginning with us, right, till now, right, we are discussed, right, you can say that I spent 1 hour and we don't see anything about Laplace equation, how to solve it, because that's the way I am switching on this video. I'm just check the thumbnail and click on that and get that, right? No, actually the Laplace equation is already solved for you. Only you have to learn only one small technique and whatever we discussed earlier. Now that we have to superimpose in a proper sense, right? Those results, whatever we obtained, and my job is done or your job is done. So let's go ahead. So here we again limiting our life in only the concept of second degree second equation only. But how we solve the Laplace equation? There are many methods to solve Laplace equation. Separation of variable technique, Fourier series, green function method, finite element method, and finite difference method. So finite element, finite difference method are the numerical approach, okay, which are a completely different ball game, right? So it depends on a lot of effort on that. So if you need something on finite element, finite difference, not in general theory wise, again it's a huge thing, right? So I'm not discussing that obviously. Now here there is a Fourier series, that video, like if you're seeing today itself, right, whatever day I uploaded it to you, right? So in that case, right, you don't see that solution. But in some time, you just subscribe to this channel so you can see those videos is coming of that, how we solve this Laplace equation using Fourier series, green function, and all that stuff, right, in upcoming days, right? So if you see when everything is uploaded, right, so then, right, obviously you check the other video solution in this playlist, you will see all those things is done, right? So if you are seeing now, please subscribe. Okay, let's go ahead. So now the solution will be in separation of variable. Now our equation system or the Laplace equation will solve here mostly in separation variable technique, which is very, very basic, and that's why as we are discussing the basic techniques today, so that's why we are go ahead with the separation of variable approach. Now, using variable of separation technique, it's not the same variable separation concept, right, used in solving ordinary differential equation. It is quite a little bit different. Let's concentrate on that. So here, first we consider a two-dimensional Laplace equation. And here, our solution is uxy. Now see that u or the solution is a function of x and y, right? So here, separation of variable means that we forcefully, now I'm saying again, we forcefully assume that the solution is the form of a function of x and a function of y separately. So xx into yy. Now, it is possible in real life all the time? No, it's not possible, right? But I'm saying that again, I am forcefully assumed it, right? And based on assumption, right, we'll proceed, right? And then we'll see the solutions, okay? So here all the assumption, a lot more assumption will be implied, okay? Let's go ahead. So here, as uxy is a solution, so therefore we need to find out that this is satisfy the PD. So therefore, right, we need to calculate what is del u del x2, what is del u del y2, and so on and so forth, right? So first we differentiate partially with respect to x. So if I define partially with respect to x, we can get that del u del x is equal to y into del x by del x, right? You can understand from that, because this thing, if I speak, right, it's something confusing, right? So it's better to go ahead with the line separately, right? Now see that, right? When I define with the differentiate with respect to x partially, the y will be treated as a constant, and that's it. Now, if I differentiate again with respect to x, we get that del 2 del x2, which is y times of del 2x del x2, and if I differentiate with respect to y, we'll get that similar approach, right? What will be our del 2u del y2? Now, whenever we calculate that, our job is to substitute it back these two expression, right, in the given equation, right? So if I substitute it in this given equation, it will be reduces to in a very simple form. Now see that, right? Here we get equation, and this equation is called that equation after applying the separation of variable technique. Now we divide both sides by xy. These are the normal approach. These approaches you have to remember always. Now first use that as a variable separation technique, then substitute that, find out the value of del u del x, del u del y, or whatever, and then divide by xy. Okay, later stage we'll see the solution in 3D as well, right? Okay, let's go ahead. Now, if I divide both sides by xy, we see that 1 by x del 2x by del x2 plus 1 by y del 2y by del y2 is equal to 0. So we can take the y value 1 by y del 2y by del y2 in the other side. So if we take that, right, we can say 1 by x del 2x by del x2 is equal to minus 1 by y del 2y by del y2. Now, as these two are equal, right, obviously we can say that this is a constant, right? Why? Because see that, right? If you say that, right, why it is a constant? Because see that it is a function of x, right? And it is a some function of y. And there's, I'm not saying it's exactly function of x and y, but whatever may be, right? Again, right, equating these variables, right? So therefore, we can say that this is constant. Okay, again, it can be an assumption, but we'll do so. So if it is a constant, right? So therefore, we consider it as a constant k. So that's again our second assumption, right? Now, if we do so, right, so therefore we get two types of equation. What's that? Del 2x del x2 is kx and del 2y del y2 is equal to minus kx, right? Now see that, concentrate on the last equation, right? Last two equation. Now in these two equation, both the equation are independent of y variable or x variable. These are only in x equation, only in y equation. So therefore, why are we discussing about the partial differential equation to make our life difficult? So therefore, as both the equation are only the variable in x and y separately. So therefore, we can say that after using the separation of variable technique, our Laplace equation or the PDE or the partial differential equation will be converted to a simple form of ordinary differential equation of the form second degree form del 2x del x2 minus kx equal to 0 and vice other way around, right? You can observe that from the screen, right? That's it. Now you understand why we solve the ordinary differential equation in that particular problem. We solve this equation as y double dash plus ky equal to sine x, or we get the complementary function in the form of other way around, right? So that's the basic approach. Okay, let's go ahead. We get the variable separated equation. Now let's go ahead. Now notice that, right? Here we recall, okay, the complementary functions of a when we solve the equation in the form of y double dash plus ky equal to 0 into fx. So here we see that, right? Here we consider, right, that c1x plus c2 when k equal to 0, and we consider that k is equal to something else, and all the stuff. Now see that we can apply this concept, whatever we used earlier, directly here. So it will happen for you only. So if you remember this, then we can solve this problem directly. Otherwise, we have to apply that particular approach, right? K greater than 0, k less than 0, and so on and so forth. Every time, right? When you solve this kind of approach, right? So that's why I say that, remember it. So whenever you use the heat equation, wave equation, everywhere, right? Then this particular technique need to be recalled again and again, right? That's why we learned it at the beginning in Laplace equation. Okay, that's it. Now here, right, we say that, right, that our x will be, its k can be positive, k can be negative, right? So therefore, we consider that when k is negative, right, what will be x? When k is positive, what will be x, right? That's it. Now let's explain that, right? Notice that, right, here k is our complementary function. Here the sign is positive, but here my sign is negative. So therefore, this will the solution of this given differential equation x, right? If minus k equal to 0, minus k is equal to lambda square, minus k equal to plus lambda square. So that's why when k is equal to lambda square, that means the positive one, right? We have to use, right, that c1 c2 case, right? For the cos, when minus k is positive, so that means k is negative, right? So that's the relation or the connection you have to make. For the next case, right, that del 2y del I2, right, we can directly use the condition as we derived, right? That's it. But notice that in both cases, I don't use the condition k equal to 0. Why? Because see that if I choose k equal to 0, so therefore our del 2x del y x2 and del 2y del y2 must be equal to 0. Now, if del 2x del x2 is equal to 0, so therefore, what is del 2x? You can say that y into del 2x del x2 and x into delta x delta y del x2 is always equal to 0. Now, therefore, the grad square u always be 0. So therefore, if I consider k equal to 0, so then, right, there are nothing to solve. It's a very, very simple trivial conditions, right? It's something like that. I'm going to solve the equation, right? That 0 into x equal to 0. So it's always 0 for whatever the case is, whatever the situation it may be, right? So it is called a trivial solutions, right? Mostly the zero solution is called trivial solution, right? So that's why, okay, that if I consider k equal to 0 case, then uxy equal to always be 0 in the entire domain, right? So that's a trivial condition. So that's we are not looking for. So that's why we don't consider that k equal to 0 conditions. So that condition is ignored. Now, we get that uxy, x, yy term by using the condition. So only one condition need to be defined, that is the boundary conditions. Let's go ahead and consider a particular boundary condition in 2D, whatever we discussed earlier, right? So here we consider specific boundary conditions, right? That's why I consider that in y-axis it will be 0. Again, it's a given condition in V, and all the other condition is in the 0, it is 0, and it is 0, right? So three sides is 0, one side is V, right? That's it. A very, very, very basic conditions, right? You get a different boundary condition here. So from here onwards, right? Whatever the problem it comes, based on that you have to choose, right, the techniques, you have to choose your problems and all that stuff. Now why we do so, right? Let's go ahead and discuss a bit, right? Now here first we have to identify the boundary conditions, right, in x and y, caps x caps y, right? Let's go ahead. So here you say that the for the boundary condition, right, uxy is xx and yy. So therefore, if I apply the first boundary condition that u0y is equal to x0 into yy, right? So therefore, this boundary condition must imply, right, x0 is equal to 0. Why? Because x0, if I don't consider it as 0, and if I consider yy is equal to 0, so its entire domain, right, the y representation, right, will be 0. So the solution is 0. It's a trivial solution. So here we are not talking about the non-trivial cases always. So that's why I'm assuming that yy is not equal to 0. If I apply the another boundary condition, that is uly is equal to xly into yy, right? Now see that from here we are not able to conclude anything, because xl may be v by 2, yy may be v by 2v, something y v by 5, 10v, right? Like whatever can be possible, right? So here, from here we cannot conclude anything, so just leave it. Now we consider the another two condition, right? ux0 is equal to xx yy based on the similar logic of non-triviality conditions, that y value is 0, and at the same thing for yn equal to 0. So we get the second boundary condition of the second and third boundary condition, that is y0 equal to 0, yn equal to 0. Okay. That's it. And one condition is already left over. So that's the four boundary conditions, right? In the form of x and y, and uly, I can't use it. So I just leave as it is. Okay. That's it. Let's go ahead. Now notice that whatever you are seeing now, the solution of x and y form, boundary condition, and the general solution in the form of uxy into is x and y. Now from here, you have to define the what value of x and y will choose. And this need to be chosen in a very tricky way. If you can do so, you don't have to give much effort. But if not, mathematically you can go ahead and obviously find out what is the solution. But now let's go ahead and discuss the tricky things first, right? Now see that here, depending on boundary condition, right, that I will say that what condition you need to choose for x and x, right? It will be k greater than 0, k less than 0. I don't know, right? Now notice that, right? If you choose first condition, right, that k minus lambda square, right? Let's go ahead in that. So if I consider that k equal to minus lambda square, that is lambda is less than 0, right? What will happen? We'll get that x and y contribution, right? Now notice that if I choose x0 equal to 0, that's the boundary condition. Let's apply that, right? So then, right, sorry, that y0 equal to 0, that boundary condition I apply first. Why? Because in the expression of y, we have two unknown constant and two given values are already there. So yeah, easy to obtain C3, C4 values, right? That's why. That's why. So if I apply the boundary condition, we say that C3, C4 equal to 0. So C4 equal to minus C3. And therefore, if I apply YL equal to 0, we say that C3 e to the power L plus C4 e to the power minus L equal to 0. If I multiply both sides by e to the power minus lambda, e to the power minus plus lambda L, right? It will be e to the power 2 lambda L plus C4 equal to 0. Now see that C4 and C3 are related with a minus sign. So if I use that relation, right, we can easily say that C3 is equal to 0. And if C3 equal to 0, obviously C4 must be 0. Now as C4 is 0 and C3 is also 0 as well. So therefore, y at enter every values of y equal to 0. So therefore, we get the solution in the domain is zero solution. So this solution we should not accept it. Okay, so it is gives you a trivial solution. So generally in this approach we will remove all the possibilities when we obtain the trivial solution. So that's why in this particular problem with this specific boundary condition, k cannot be less than 0. Now for your problem, some other boundary condition, it may be possible that k is less than 0, right? We are not sure, right? So that only you have to decide for case-wise study or little bit uh, you have your thinking capability. That will come when you discuss many problems by your own. Okay, that's it. Go ahead. We consider the last boundary condition, that is k equal to lambda square, because we remove that k equal to minus lambda square status, right? Because that is not useful in this particular process, right? Let's go ahead. So here we consider the case k equal to lambda square, which is greater than 0, right? Let's go ahead. So here we consider first y equal to 0 condition. So see that in this approach we can say that C3 cos 0 plus C4 sin 0, which is 0 equal to 0, which implies C3 equal to 0. If C3 is 0, our y is become C4 sin lambda y. That's obvious, right? Now we have to apply another boundary condition, that is YL equal to 0. So if I apply YL equal to 0, it is gives me that YL is equal to C4 sin lambda L equal to 0, which imply that sin lambda L is equal to 0. Why? Because if I take C4 equal to 0, it's the same problem of triviality. C3 0, C4 0, Y 0, that's it. So to get non-trivial solution, we assume C4 is not equal to 0 and hence sine lambda L equal to 0. Now go for the class school level. It's a trigonometric equation. General solution. If sine x equal to sine theta, right, or sine x equal to 0, take specificity. So it is n pi, right? So therefore the general solution will be lambda L equal to n pi. N belongs to the z and lambda is equal to n pi divided by L, right? That's it. So this is called the values of lambda. Let's go ahead. So now our y, that solution, will take the form of C4 sine n pi by L into y. So this is called the y values. So y value is obtained. Now we have to find the expression of x. To find the x expression, we consider the x, right? X equal to 0 condition. So therefore, C1 e to the power 0 and C2 e to the power 0, 0. So C1 and C2 is 0 and C1 equal to minus C2, which imply that our expression x will be equal to C1 e to the power lambda x minus C1 e to the power minus lambda x. That's it. So therefore, our solution can be written as xx is equal to c1 e to the power or exponential lambda is well known n pi by L. So n pi x divided by L and n minus n pi x divided by L. That's it. So we obtained x, we obtained y. Now, if I multiply by that too, so we get the general solution. So we obtain the general solution. So now let's go ahead. So here, right, we rewrite our uxy as a product of x and y, right? So it's an into e to the power something and all that. So here we recall one formula, okay? That's called that sine hyperbolic x. So we know that sine hyperbolic x is equal to, this is hyperbolic, okay? So it will be e to the power x minus e to the power minus x divided by 2, okay? So if we use that, whatever there inside the curly bracket, that will be converted to, right, that an is equal to 2 sine hyperbolic n pi x into 2 sine hyperbolic n pi by 1, okay? That's it. Now notice that particular solution of uxy you obtained, right, it is true for n equal to 1, n equal to 2, n equal to 3, and so on and so forth up to infinity. So therefore, right, we can say that, right, if I redefine that un, right, so u1, u2, u3, u4 dot dot up to u infinity, all are the solution of the Laplace equation. So now in OD and in PD, there is a theorem states that if U1, U2, U3 or whatever, right, is the solution of a OD or PD, therefore, any linear combination of them will be the solution of the original differential equation. So that's why we say that as U1, U2, U3 are the solution, so summation of them is also a solution, and that's it. So we are saying the summation of an and all the expression from n equal to 1 to infinity is the solution. Now see that here, to obtain this particular solution, all the boundary condition, we actually applied it. So therefore, in the unknown constant cannot be present. It should be in numerical values, right? Or some expression should be provided. Otherwise, we can't say that. So here, we are not able to write the general solution. It must be a particular solution. We wrote it as general solution. Why? Because to explain it. But as the boundary condition is involved, so therefore it cannot be general. It should be particular solution. And if it's a particular solution, an cannot be present. The value need to be present. So basically we need to evaluate the value of an. So let's go ahead and try to derive this value. And this concept, whatever we are saying, in general, it's called normal mode theory. So using normal mode theory, we are adding out all those things, and each individual, right, is called the nth mode contribution. So basically that an sine hyperbolic n pi by L and all that, it's called the nth mode. So for different values of x and for different values of y, right? For n equal to 1, we get the first mode. For n equal to 2 is the second mode, and so on and so forth. And n pi by L is known as the mode number. So therefore, if you're talking about a wave, it's called wave number, okay? And some for something else, like for heat, it may be heat conductivity or something else, I'm not sure. But I'm saying that for different physical perspective, it may be electronics, it may be electrostatics, it may be ocean engineering, it may be mechanical, proper wave equation, sound wave, whatever, right? This mode number will rename differently, okay? But the concept wise is the same, okay? Let's go ahead. To find out the values of an, right, we need to apply one important step in this approach that's called orthogonality properties or orthonormal property, you can say, right? Let's go ahead. So here we notice that only one boundary condition is left behind. That is ULY is equal to V. That condition we don't use yet, right? We only use X0, Y0, YL and all that. So we apply that. So if I apply that condition, right, we say the summation of everything in the right hand side is equal to V, right? Now here, from here we need to find the summation, calculate the value of A1, A2, A3 and V. See that this is not possible. That how can you go ahead? So for that, whatever I said earlier, that orthogonal orthonormal properties need to be used. Let's see how we apply that. So now we consider the last step, right, and apply the or rewrite that as a summation of everything. So now let's see that here, right? We write down that summation of n equal to 1 to infinity in a from a1 to an, and each term is right written down. Okay, that's it. Now notice the orthogonal property. It says that integration 0 to L sine I pi y L into sine j pi y L, right, divided by L actually is will be 0 if I is not equal to j, and if it is equal, right, so therefore it is L by 2. Okay, so this is nothing, right? You can take this integration, right, and do this, right, by the sine 2 theta concept, like sine A sine B, sine A plus B by 2 and all that. So based on that normal integration, right, technique, if you trying to find out the definite integration, you will get the answer, right? Nothing else. So take I equal to j, so it will be sine squared I pi y by L, that will be L by 2 using the cos 2 theta formula, or go ahead with that. So that's your job, right? Now, here, if we apply that, why we are using that? So the first step will be multiply both sides by sine I pi y divided by L, okay? And integrate with respect to y, right? So this is the step. Let's go ahead and discuss that step by step. Now see that here I am multiplying by I pi y. So basically we are multiplying by 0 to L, whatever there in this expression, multiplied by sine I pi y divided by L. Let's concentrate on this term, right? See that we have 1 pi y, and here we are having I pi. So see that when I and j are different, it's 0. So this term will omitted, this term will omitted by the as we multiply that. So if we perform the integration, it will be 0. This term will be multiplied. So only this term will be left behind, because here we have I pi y, here we have I pi y multiplication. So therefore, we can rewrite that in this particular form. So ai sine 2 sine hyperbolic I pi is constant. So it came out from that I pi is came out from that integration sign. We multiply 0 to I sine product, and v multiplied by 0 to pi the integration. And that's it. Now see that the left hand side, the integration gives L by 2. Now we have to perform the integration in the right hand side. So that's a normal sine m pi by x, right? Apply the definite integration formula. So if I apply that, right, to 0 to L and apply this process, right, it will come back as v by I pi cos I pi minus cos 0, right? That's a normal technique. So therefore we obtain that ai is equal to some form like b by something into 1 minus cos I pi, right? That's it. So now see, ai is obtained, right? So now why we are looking for n only, right? So just replace I by n. That's it. So if I do so, right, we get our general expression for that constant term. So therefore, we get the particular solution. So therefore, we get our particular solution now. So substitute that an value in the summation form, right? And then our job is done. Okay. Okay. So now see, right, this summation of this unknown constant can be rewritten with some small extra calculation. See that cosine pi can be minus 1 whole to the power n. So now see, when minus 1 whole to the power n, so therefore we can say that n will be 0 when n is a even number, because minus 1 whole to the power even is plus 1, it's cancelled out, it's 0. So it will be 0. If it is odd, right, so therefore it come back with a v2 by n pi sine pi. That's a normal calculation. Do it. It's not that kind of difficulties, right? Because you can observe that here it will be 2 minus 1 will be cancelled, so it will be 2. So 2v n pi I sine hyperbolic pi, right? That's it. So this is our job, right? And let's go ahead. So now notice carefully. So therefore you can say that, right, our coefficient when n is a even number is 0. So therefore in uxy, the final general solution, right, there will be no even number terms like a1, a2, a4, a6, a7, a8 is not there, right? All are odd, right? And for odd, it is 2v by n pi. So therefore, we say that our final solution will be 4v by pi, right? Just multiply by 2 sine hyperbolic with that and write the sum. That's a very normal job. And then we get uxy. Now here I wrote it as summation odd. That means that n value need to be considered here. That is odd terms. And that's ends the solution or the general solution or the particular solution of the Laplace equation. So this summation is actually gives us the solution of our problem. That's it. Now let's go ahead. So this is the solution. So if the boundary condition is changed, then we have to start from the basic, right? That we say that uxy, xy and all the stuff. So which k greater than 0 and condition will be started and so on and so forth, right? For different boundary condition, Newman, Dirichlet and all the stuff, right? We have to, or you have to proceed on that particular approach. Okay, that's it. Let's go ahead. Now, our job is to interpret the result. So that's the last aspect. So mostly this thing is required, right? If you are a research scholar, PhD scholar, if you want to become on that, right? So how we interpret the result. I'm not doing a very high level interpretation, just basic to like understand your concept, right? Let's go ahead. So here we get the general solution and for the boundary condition. So here, right, to make our life simple, right, see that here the v, right, the value I consider it as 10, okay? So that like v I can't process, right? So here I consider that v value is 10, okay? That's it. So therefore, we can write this particular small MATLAB code, right? So here we say v equal to 10, l equal to 5, that it is bounded by 0 to 4, 0 to 5, 0 to 5, okay? And we define or we create a mesh grid, right, from 0 to L with the increment size 1. So what that means, so if it is 0 to L, that means 5, 0 to 5, and we divide it, right, by a mesh, right? So it's a grid, right? So that's we performed using this line. Now we have to perform the summation, right? So this we did in this approach, right? So for n equal to 1 to 50, right? I added up, right, all the values, right? So basically in 1, 2, because we are taking the odd numbers only. So here we are adding this particular step, right? Each and every line. So that will be gives us the sum, okay? And then we just add the final sum, and each sum, each end, right, will give us the modes. Let's go ahead. So this is n is equal to 1. So this mode, this is the called the mode or the modal distribution, right? Or mode shapes, right? For the Laplace equation with that typical boundary conditions, right? So what happened then, right? Do you recall that boundary condition? Yes, let's go ahead. So see that, right? Our boundary condition says that, right? 0, 0, 0, and 10, right? That's the boundary condition. Now notice here, right, based on the contour, right, everywhere it is 0, right? It's obvious, right? This is 0, this is 0, this is 0. But in this side, right, it should be 10, right? Now if you see the color, right, here we have 10 is this particular color. Mostly we satisfy this color, right? But see that it's not true everywhere, right? Now we'll come to that later. So this is called the modal distribution, right? Let's go ahead for the third mode. Why third mode? Because in third mode, right? In the third mode, right, we can easily observe, right, that 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 the distribution, right, is changing, right? And also why it is third mode, because always remember that, right, that whenever you see the mode shape, right, it will be easily understood by number of zero crossing, right? What is the meaning of number of zero crossing? Forget about everything. I'm talking about this 1D, right? It's a vibrational problem if you think the basic engineering. So see that first mode means this shape. It's a sine curve, right? Sine shape curve. Second mode means that something like that. We have a two crossing. Third mode, right, it will have the three crossing. Okay, that's it. Now see that here, if we take these shapes, right, all the contour will satisfy this particular shapes. If we see that it will take this shape, now it will be come back in other way around, then come back. Now why we do so in this way? Because see that when we plot, we take the real part and the imaginary part. So here we plotted using the absolute function, so that negative positive will come back in xy approach, right? So that's why we are taking this thing, right? Don't believe it? See the 5. So if it is n equal to 5, see that how many brand do you get? 1, 2, 3, 4, 5, right? So it's fifth mode. So by observation of the each mode, we can understand what will be the mode. So if there is a problem in code, or if you interpret the result by the basic of the visualization, you can easily identify. You can easily identify that mode number. If there is an issue, so we made a mistake. Let's go ahead and understand the few shifts, right? So this phenomena is true good, right? Now see that whenever you are go ahead and add more and more modes, right, our final result, right, or the uxy, right, is actually converging to a particular solution, right? So mode 1 only is not the solution. Mode 1 plus mode 2 not the solution, but mode 1 plus mode 2 plus mode 3 plus mode 100 mode 200 will gives you the solution, and that's the normal mode theory. So if we add all those solutions, so then we get our final solution in this approach, right? So see that this is actually the final solution of uxy when we add up to 50 modes here, right? Obviously in code or anywhere in real life, 50 types of mode, infinite modes cannot be added. That's a theoretical concept. But we added only 50. You can go ahead with 100, 200, all that stuff. That's okay, right? But our solution need to be converged. Now see that, right? Now, if we see the solution, right, all the boundary condition is satisfied, 0, 0, 0. Now see the color here in this boundary, right? That boundary color will be very similar to the color at 10. So what that means, right, that our temperature distribution in such a way, or not temperature, the whatever the values, right, that distribution will be something like that, right? The all sides, right, the boundary is 0, that is provided, and the rightmost side, right, is 10. So this is the solution, right? So if I see the very close loop, right, on this approach, right, on this approach, right, on this side, right, we can see that it is 10, but in built we have different kind of bands, but that bands is also very close to 10, right? So these are the errors, little bit of errors, right? Or in this particular concept I'm saying, why? For different problem or different physical consequences, right, may that bit is be true, right? But why this type of small errors and everything is observed? Because see that, right? If there is a temperature, if this is something, it's a boundary. But technically, right, that boundary should not be fixed by something, right? It will vibrate little bit. It will have the little bit temperature changes. So that is also can be considered here, right? For different problem, like if you're solving the acoustic wave and all the stuff. So this is the meaning is different, right? So this is the interpretation of Laplace equation, right? Now here we can interpret much more. Why? Because we don't know what's the physical quantity we solve. So this physical understanding will be much more clear when we solve heat equation, wave equation, and so on and so forth. Okay, that's it. Now we take about some exercises. Now, if you want, you can solve this particular, the same problem with different boundary conditions, right? So now notice that here our all condition are same, but instead of putting that zero condition here, we put our unknown constant, unknown variable here. It may be sine, cos, and all that stuff, right? That's it. So this is another one type of equation. You can take a screenshot or take a pause, take that note, and try to solve this equation. Okay, if you want to. Let's go ahead. Go ahead for the second one. So here, right, with that, right, we show you two problems, right? Now, with that, we can solve whatever the problems you have, right? You can solve with that, right? Now, if you love this lecture and if you want the exercise problem to be solved, right, please comment below. We'll solve that also, right? Or if you want, right, some things you learn from our side, and if you have some doubt, right, please comment, and also you can mail at dcacademymaths@gmail.com so that we can make a video in doubt clearance, right? So that we can clear those basic doubts, right? So that's it. So that's it from my side and from our side. And please subscribe and keep learning on this particular aspect of wave equation and the remaining. So in the upcoming days, okay, or the remaining videos, you can see that in few days come in the updates, right? You'll see we'll upload heat equation, wave equation, then green function, Fourier transform, Laplace transform, and the basic thing on this approach, right? And obviously, little days we will also solve the 3D wave equation, 3D Laplace equation in spherical coordinate and all that stuff, right? But obviously, it is down the line, right? So subscribe and stay with us so that you learn much more, gain in a very, very basic way, right? Our main aim is not to jump, right? So that see that we already spent approximately 2 hours only for Laplace equation, right? But hopefully you learn little bit from our side. If you learn little bit, that's the benefit or beneficially for our case, right? That's it. But obviously, for any other stuff, heat equation, wave equation, all that, it will be much more faster because we don't solve that all the concept you learn in this particular lecture. That's it. So that's it from my side. You hope you learn something from our side. See you in next video. Thank you.